Welcome to the Foundry by Forge College. For this explainer, we're going to go ahead and put away that perfectly optimized, highly theoretical mining spreadsheet you've been staring at. It's time to step into the messy, heat-soaked physical realities of actually operating this hardware.
Picking up right where we left off in our previous lesson on calculating costs and ROI, we need to have a friendly but honestly absolutely crucial reality check about what really goes down when you finally turn these machines on. Because as it turns out, thermodynamics literally does not care about your financial projections.
Okay, so here's our blueprint for an engineer's audit of your mining setup. We're going to cover 1. A reality check on efficiency. 2. Demystifying the core metrics. 3. Real-world versus data sheets. 4. Hardware tuning and optimization. And 5. Automating your efficiency math. Section 1. Reality check on efficiency. So why exactly do we need to measure hardware efficiency in the physical world instead of just trusting the shiny numbers printed on the box? Well, while our previous explainer focused heavily on capex, the cost of actually buying the gear, today we're looking strictly at operating expenses, or OPEX. This is the brutal arena where accumulating dust, random voltage drops, and those sweltering summer afternoons all gang up to just ruin your theoretical efficiency. Moving on to Section 2. Demystifying the core metrics. To figure out our actual operating efficiency and fight back against all those elements, we need to look at the diagnostic gauges on our dashboard. Think of this kind of like checking the miles per gallon in your car. First up, we have hashes per watt, which is, well, exactly what it sounds like. It measures the sheer computational horsepower you're getting for every single watt of electricity you're burning. The higher this number, the harder your power is working for you. Now, on the other side of the coin is joules per terahash. While hashes per watt looks at speed per unit of power, this metric looks at the energy consumed per unit of work. It's a highly standardized, compact little metric you're going to see plastered on absolutely every single product data sheet out there. For example, let's say a device is producing 100 terahashes per second while consuming 3,300 watts. Since 1 watt is 1 joule per second, your resulting efficiency is a clean 33 joules per terahash. And remember, in this game, you want that number to be as low as humanly possible.
Section 3. Real-world versus data sheets. Now it's time to compare those perfectly pristine manufacturer data sheets to the messy reality of a physical server rack.
Okay, so before we can start pointing fingers and declaring a machine inefficient, we've got to measure it correctly. That means collecting steady-state data over a 1 to 5 minute window, but only once the machine is fully warmed up. To do this right, you need a calibrated power meter, a solid log of the ambient room conditions, and the hash rate pulled directly from the device's API.
Let's take a look at some real clipboard data from an audit of 3 identical ASIC units sitting literally right next to each other in a rack. Notice how A601 is hitting that perfect 33 joules per terahash, but A602 and A603, they're drifting higher. They're actually consuming more power for essentially the exact same output. Crazy, right?
But keep in mind, our clipboard is only showing us device-level efficiency. To get your true operating costs, you've also got to factor in system-level drains. We're talking about those massive cooling fans on your walls, power supply inefficiencies, and just the overall facility power usage effectiveness.
Looking closely back at our audit, though, we have to ask a really critical engineer's question. Why on earth is A603 drawing significantly more power, like 3,600 watts, for almost the exact same output as A601?
Which brings us to Section 4, Hardware Tuning and Optimization. The absolutely crucial point here is that once we spot a degraded efficiency metric like that, we don't just throw up our hands and accept our fate. No way. We step in as engineers and start actively tuning the hardware. We've got several levers we can pull. For instance, if we discover A603 is running 10 degrees hotter just because it drew the short straw and got placed at the top of the rack, we adjust our thermal management. Otherwise, we might explore firmware tuning, frequency calibration, or even undervolting the power supply to forcefully whip its efficiency back into shape. All right, Section 5, Automating your efficiency math. Let's see how this all builds into an automated diagnostic workflow, because I can promise you, crunching these numbers manually on a clipboard for thousands of screaming rigs, that is a fast track to completely losing your mind. You can actually just build a small Python script, let's call it something like efficiency_calc.py, that automatically ingests all your raw power data, calculates the steady-state metrics, and outputs your adjusted joules per TH figures in real time. It literally saves you incredible amounts of manual effort.
And a simple script like this instantly proves how even a tiny tweak in joules per terahash dramatically changes your monthly energy consumption. This lets you feed accurate, reality-based numbers straight back into the financial ROI models we built previously. It's a practice we highly encourage as you progress through Forge College's wider curriculum. Plus, it significantly lowers your environmental emissions footprint, which is always a win.
If you take nothing else away today, treat this as the golden rule of managing mining operations. You know, data sheets sell products, but measured steady-state values, those dictate whether your business actually survives and thrives.
Conclusion. Ready for the heat? We have now successfully bridged the gap between theoretical math and the actual hands-on process of conducting a hardware audit.
So, I'm going to leave you with this provocative thought to ponder before our next explainer, where we tackle environmental impacts. If ambient temperatures spike 20 degrees tomorrow, how fast would your real-world ROI just melt away? And more importantly, do you have the tuning strategies ready to save it?
Be sure to visit the Forge.College website to learn more about this subject, access our scripts, and explore a ton of other fascinating Web3 topics. I've had a blast guiding you on this journey, and I will see you in the next explainer. Keep exploring and optimizing.